The three additional topics I'll talk about very briefly now, but it's of course probably what drives a lot of your interest. The geomechanics of shale gas and tight oil production. Over the last decade or so, shale gas, as shown in green, shown in red on this map, has been very active. 150,000 wells, have been drilled in North America to produce natural gas from horizontal wells using a multi-stage hydraulic fracturing. We've been working in the areas where the checks and the plus symbols are, so we've been gaining a lot of valuable experience. The areas shown in greenish red are where both gas and liquids are being produced, and the areas shown in green are some of the areas where there's tight oil and horizontal drilling and multi-stage fracturing are used for that. So we've been pretty busy. Now, you have to understand that these rocks are very unusual. This is an SEM of the Eagleford Shale from workers in my research group, and this is kerogen, the waxy organic substance from which the hydrocarbons are derived. We zoom in and we can start to see some pits in the kerogen. We zoom in some more, and these are the pores through which the hydrocarbons are flowing on the order of a couple hundred nanometers. And these rocks have permeabilities that are about 1,000,000 times smaller than a conventional reservoir. That's what's kept the hydrocarbons in place for such long periods of time. And this is why we use horizontal drilling and multi-stage hydraulic fracturing. And here's a study from Dan Moose and others. A well is drilled in the direction of the minimum stress. It's hydraulically fractured multiple times from the toe to the heel. The dots represent very small microseismic events. A magnitude -2 microseismic event is slip on a fault that's less than 1 meter in size, and it slips about 1/10 of a millimeter. Okay, very small events, but they show a cloud of where pore pressure has affected the rocks surrounding the hydrofrac and where these little slip events have occurred. And this process enables us to produce hydrocarbons in an economically viable way. However, while there have been 150,000 wells drilled and 30,000 more wells will be drilled this year, and while it's economic to do so, we don't do a very good job. In the dry gas reservoirs, we recover about 25% of the natural gas, and in the liquid systems, we're recovering maybe 5% of the liquid hydrocarbons. We need to do much better. So while we understand this in sort of a heuristic way, we're not doing a very good job in an objective way, and there's a long way from where we are to where we want to be in terms of optimizing this process. And this is what's driving the research in my group and in other groups at this university and many others. And so over the past few years, we've been studying and publishing papers on the physical properties of the shale reservoir rocks, on the fact that there's a lot of slowly slipping faults in these reservoirs at the same time these microseismic events are occurring. We've studied why the slow slip is occurring, and we've been studying fluid transport at the nanoscale. Viscoplasticity, I said, was important. It's very important in these clay-rich organic rocks, and we're trying to build some better discrete fracture network models. The final topic we'll talk about is triggered seismicity. In the last few years, this is from a paper I published in 2011, pointing to earthquakes triggered by fluid injection in Youngstown, Ohio, Guy, Arkansas, Dallas, Fort Worth, the Colorado-New Mexico border near Raton. And then subsequently, it was argued that some earthquakes at the end of 2011 near a city in central Oklahoma were also triggered. In each of these cases, it's not hydraulic fracturing, but it's the injection of wastewater from the hydraulic fracturing process that's caused these earthquakes. There was some mild damage in a couple of these cases. Fortunately, nobody was injured, but they are of great concern. And so while wastewater injection has been going on for many decades, in fact, there are 150,000 EPA Class 2 injection wells operating in the United States, and there have been a handful of cases, the incidence of triggered seismicity is increasing. A recent article by Bill Ellsworth showing kind of the numbers of earthquakes in this central and eastern United States demonstrate that, starting in about the early 2000s, about when shale gas development was getting going in the Barnett Shale in Texas, the number of earthquakes in this region have been increasing dramatically. And so we are challenged by the need to control this environmental problem. And I'll walk you through how we kind of frame this problem, how we work on it. I wrote a paper for the general public last year in 2012 on this topic, on managing triggered seismicity, borrowing a concept from the geothermal industry, a stoplight type system. Hey, we're monitoring everything, not much is happening, everything is good. We're monitoring everything, something is happening, we need to know more. We're monitoring everything, something is happening that looks like it could be potentially problematic, and we better stop. And we will develop through the course and then apply in this very last lecture the techniques for doing that. And those techniques mean understanding the stress, understanding the mechanics, and understanding whether or not that fault is going to slip in response to a fluid perturbation. And we know how to do that. In fact, in this particular case, which is over here in central Arkansas, we have a very good knowledge of the stress state. We can see a style of faulting consistent with first principles, and we can see something developing that was very scary and very problematic, and stopping injection was the most important thing to do, which was done, and the earthquakes went away. So we know basically how to manage the problem, but we need good data and we need a scientific approach to do it. So that's going to be the next 19 weeks. We'll see you next time, and we'll jump right into Chapter 1. Thank you very much.